Okay, so we're continuing with trigonometric integrals, this time secant and tangent. We're going to solve these 5 problems using these guidelines. We're going to use the first, second, third. We're not going to practice number 4 here because this refers to whenever secant has odd power. Oh, you can't see that, can you? Here for number 4, whenever secant has odd power, like secant cube x, I have a separate video on that, so you can watch secant cube x there, because that's kind of needs a separate video of it on its own. But 5, we are gonna 5 is gonna be 5 here. Okay, so let's start. Let's solve this, but let's first chat about it. Which rule would you use? So it says, the first one says that secant has even power, then use first rule. Okay, so secant has even power, positive and even. So we could use first rule. But the second says that if tangent has odd power, then use second rule, positive and odd, which here it has tangent has odd, positive, odd power. We could go with second. So which one should we do? Well, we'll do both. First, let's go with first, I guess. And then we'll do the second. And we'll see that we're going to get 2 different answers that are going to be actually the same. And we're going to also prove that. So it's going to be lots of fun. So as soon as you decide which rule to go with, and in this case, I decided to go with secant has even power, which it does indeed here, then you're given, it's kind of an algorithm, like if this is checked off, and it is, then you go and do a first bullet point, convert it to tangent, and then save secant square x to du. It's like, it gives you a to-do list, right? So I'm gonna do just that. And in order for me to convert secant to tangent, I'm going to write it as secant square, because that's going to be the relationship. Okay. Now let me remind you something that you're going to use all the time with trigonometric integrals involving tangents and secants. Remember, with cosines and sines, you used this very fundamental relationship that came from Pythagorean theorem here. Well, if you follow the math here, you get this relationship. It's an important trig identity that actually comes from this very important relationship. So write this somewhere and then express secant square x and tangent square x, and you're going to use that all the time like I have here. I'm actually going to copy it and then paste it with whichever problem we're solving. Because whenever it says converted to tangent, secant square has this sort of relationship to tangent. So that's what it asks you to do. So I'm going to do that. First secant square gets converted. Okay, now I have 1 secant square x. I need to put that, secant square x, I need to put that away for du. And then I also have tangent cube x. dx. Now you're going to multiply through. So you're going to have 2 terms being added, right? Because when you multiply this by, you'll have 2 terms being added. Therefore, you can have 2 separate integrals, because anytime you have a sum inside of the integral, you can take integrals of sum. You combine and add powers of tangent, because you can do that, so why not? In the first case, it's 5. So as I said, I'm going to write it as separate integrals. So everybody gets their very own dx. Okay, so at this point I have checked off all the boxes. So I did convert it to tangent here, and then I kept secant square x, and that kind of consumed all the secants that I had, which is secant raised to the fourth power. And if I had 6, then I would have it square there, and then you would need to do a square of the binomial, but I don't because I had 4. Okay, so now I'm ready for u substitution. They told me that this needed to be saved for du, and I trust that they didn't lie to me that that would be du. So then u should be tangent, right? And in fact, derivative of tangent, I kind of have this here as a reminder. Derivative of tangent is secant square x. The whole reason why this exists, trigonometric rules for secant and tangent, is because they're each other's derivatives and each other's integrals. They kind of go in a circle the way that sine and cosine do. So that's why. And just like it was the case with sines and cosines, you always ended up with simple power rule integral. We're going to end up with power rules here as well. I'm going to back substitute. I told you that in this problem, you could either follow first, which is something we did together, or the second guideline, which says that tangent has odd and positive power, which it does, so we could do either. Now I'm going to show you how you would solve it if you follow the second rule. Okay, let's follow it slowly together. So we're going with this now. Power of tangent is odd, okay. Then convert tangent to secant and keep secant tangent for du, okay. This is the second guideline. So secant tangent for du. So I had 3 tangents, so I needed to convert this, because you can't convert tangent in first power to secant because that's not the relationship here, right? Tangent square x is secant square x minus 1. So that is what you need to rewrite tangent square x as. And then this one was raised to the fourth power, and I borrowed 1 secant from that because I needed it for du. And then that was left with raised to the cube, and I multiplied it through and I separated the integral, took separate integrals. In this case, u was secant x and du was this. Again, power rule, but the answer here was not tangents but secants. And my question is, do you think that these two expressions are the same? And obviously they are the same because they're the answers to the same integral. You can always kind of do the math and go from here to here, or from tangents to secants. I can't promise that you're going to get the same constants. Most of the time you're not, but you're going to get this expression if you do the math right. And I have done it here. Let me get it ready for you to screenshot. If you're curious, you can follow this or you can skip it. I'm going to go through it quickly. So I started with this answer from the second way, going with odd power of tangent, okay? And then I went and I got this. Secant square is the one that connects the tangent square. So I wanted to write it as secant square. This was raised to the 6th power, so this is cubed and this is squared. Now, who remembers cube of binomial? Probably nobody, but you can look it up. And then this is the formula. And then you square this, and that's here. And then inevitably, there's going to be terms that will be similar. I wanted to kind of write that in the same denominator, so I made sure that they had the same denominator here, 12. So I opened the brackets, changed the signs here, minus, 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 and then I canceled or combined. These canceled, but the rest I combined, and here this one didn't have a match. And sometimes this term is terms that don't have a match is easy to forget, at least for me. So I said, don't forget me here. And then all in all, I got the same answer that we did when we solved it together in the first way. And of course, I got the different constant, and who knows if I got a different constant? Who knows what the constant was here, right? But I got that constant that I lumped together in C. It told me it didn't mind that. So yeah, math works. You can get the same answer through this sort of algebra, which is a great practice if you want to do it. Okay, now solving the second problem, let's see which rule we're going to use. Okay, if tangent does not have its buddy secant and it's raised to the even power, then do this. Convert it to secants, and maybe you'll have to do it twice, it said. Okay, so let's do that. So this first tangent square x, I'm going to express that as what it equals to, which is secant square x minus 1. And I'm actually going to keep this tangent square x here, and I'm going to do that in the next step. Multiply this through. The guideline said that you may have to do this twice, which here we need to do this again. Express it as secant square x minus 1, because if this was squared here, then we would only have to do it once, but it's raised to the 4th power, so I need to do this again. The first interval is kind of ready to take, so I'm not going to worry about that. And here I can also separate these integrals, but don't forget that this minus sign will turn it into positive. First interval will need a u sub, okay? Oh, and it will also need a dx. Let me write tangent square x first. So this is du, where u is tangent, and u square is tangent square. So I have u square du, because derivative of tangent is secant square x. Antiderivative of secant square x is tangent. I'm going to take all these integrals in the same step, so that will be, but I need to back substitute, right? U is tangent, so I'll do it at this step. Minus tangent x. Okay, that's the final answer. Here, the question you ask is, whose derivative is secant square x? That's the answer to that integral, because that's you're taking antiderivative. Now, secant raised to the even power, it's so much simpler than secant raised to the odd power. You know, secant cubed takes so long to solve. I wrote this secant square x as secant square x times secant square x, right? This is secant square x, because that equals to 1 plus tangent square x. And now I'm going to multiply it through, and I'm pretty much done. If only secant raised to the odd power was this simple, that would be lovely, but of course it's not. So the first integral is tangent x, plus here you need to do a u sub where your tangent is u and secant square x is du. Rewrite this as a u sub and take power rule. Back substitute tangent. And that's the final answer. It looks similar to when you took tangent raised to the fourth power, but a little different. Now this is quite tricky, and the only reason why it is tricky is because of the fraction being a power of secant x. And here we only have this option to go with because this would demand that secant is even and positive, and secant here is raised to the negative 1/2 power, so that's not positive. So I have to go with tangent is odd, so I need to go with the second. And the guideline is that you convert it to secant and you save secant tangent for du, which is what I'm going to do. How am I going to come up with secant in the denominator? Here I have square root of secant, but it's also in the denominator. So how am I going to come up with secant in the denominator? We'll see that. Because the guideline tells me that I would need that, right? And it also tells me that I need to convert tangent into secant, which tangent square would convert to secant, right? So I'm going to write that as tangent square times tangent x. And now I'm going to bring secant upstairs, and I'm going to write it as negative 1/2 x. And that's still not secant x, right? So I'm going to do the following. I'm going to multiply everything by secant x, which is what I need in the denominator. But if I do that, I have to divide everything by secant x as well. This way, at least I got secant in the denominator, but I also got secant in the denominator, which I didn't need, but I had to do that. Oh, and this tangent square, I can already rewrite that as square x minus 1. Then this tangent, okay, I'll put that here. And now I'm going to bring this up. This term is here. This term is this one. So I can combine this these powers here, right? And that is negative 3/2. Okay? And this tangent, I want to put that with secant because I'm going to use them for du. Okay, so now I can multiply this secant through here. And I will have to combine 2 plus minus 3/2. And you need to copy and paste that here. You could have done multiplying all of this through, because you wouldn't be combining this secant with these, because you kind of need that tucked away for du. But I'm going to do that in a separate step. Okay, if you do math here, you will have 4/2, and that will be secant to the positive 1/2 power. And then now you can multiply these through so that you can write 2 separate integrals, right? And it may be tempting at this point to combine the powers of this secant, which is 1, with that, but please don't do it, because you need that secant x tangent x as a one unit, because both of them are going to be used for du. At this point, you are ready for a u sub. And for both integrals, u is going to be secant x. And du is going to be derivative of secant x, which is secant x, tangent x, dx. And this is why we were kind of treating this as untouchable and being very protective of it, because you need this du for both integrals to turn them into, after you do a u sub, to take a power rule, right? As I know that whenever you have fractions, it is kind of a complicated integral, but treat this as n and then add 1 and then divide it by the same, and then treat this as n and then add 1 and divide by the same. So have plus 1. Okay, this is 3/2. This is 3/2. And then if you had 3/2 here, 2 would come up here, right? And then u negative 3/2 plus 1. So this is 2/2 minus 3/2 plus 2/2. That is minus 1/2. Also divided by minus 1/2, right? Plus constant of integration. The last thing left to do is back substitute secant x for u. And you can maybe put the secant here instead of having it in the negative power. And that's your final answer. Okay, final one, number 5. We're going to follow the 5th guideline, which says that if nothing else works, okay, so tangent doesn't have odd power or positive power, and secant is raised to the first power, it's not even. Then, if none of the first 4 guidelines applies, try converting sines and cosines. Try converting secants and tangents to sines and cosines, which is what I'm going to do here. So secant is 1 over cosine, and 1 over tangent square is 1 over sine over cosine, or also 1 over tangent is cotangent, right? So I can write cotangent square x here, or I can write cosine square x over sine square x, which is cotangent square. This is secant x. And this is 1 over. Okay, now let's see what happens. We have cosine square here, and then cosine x there. They cancel. So let me rewrite what I have left here. And sine square x dx in the denominator. Okay, I can solve that integral, because if I said that sine was u, then my du is sitting in the denominator, which is ideal for me. Anytime I can say that whatever is sitting in the denominator is u, and I don't care about the power, as long as I have du sitting in the denominator, and I do here. This is du. So what I have here is u raised to the negative 2 power, right? Because sine is u, and then you bring that up with a negative. And that is minus u minus 1. You back substitute. You can say negative 1 over sine, which also equals to cosecant. And that's the final answer using the fifth rule. If nothing else works, then convert secant and tangent in cosines and sines, and then see if something nice happens in here. As soon as we did that, things got canceled, and then we were able to see that, oh, sine's derivative is cosine dx, and it's sitting in the denominator, and this is simply u squared. You bring that here, and then you say u minus 2 plus 1 over. There will be minus 1 in the denominator, that comes here, and then you can put that, yeah, there you go. Hopefully this was helpful.